In this video, we look at optimal receiver for the binary modulation in AWGN channels. Here, binary modulation means binary pulse modulation. AWGN means additive wide Gaussian noise. Suppose the channel is ideal. The received signal is SMT, that's the pulse we transmitted. And at the receiver, we add the noise now. M equals to 1 or 2, depending on digital 0, 1 is transmitted or digital 0 is transmitted. The channel is modeled as ideal, is a constant equals to 1. So this is a received waveform. This is a transmitted waveform. This is a pulse. And this is a random process because N of t, the noise is random. And adding time become a random process. This random process is modeled as a wide Gaussian, and the power spectral density is constant, is equals to N naught divided by 2. If needed, please review the topic of the white noise in the random process. Because this noise term, the received signal is corrupted. At the receiver, we do not have the capability to determine what is the correct waveform 100% now. What best we can do, that's the topic. We want to find the optimal receiver to minimize the probability of error. The error is defined as if waveform S1 is transmitted, which means digital 1 is transmitted, but as a receiver somehow is determined that waveform S2 is transmitted. In this case, the receiver made an error. We want to minimize the probability of such errors. I want to point it out that this relationship is on the condition of a modulation and demodulation has been performed perfectly. Here we have bit stream here. We perform pulse modulation. So the waveform is SMT, M equals 1 or 2. This is digital 1. And this is digital 0. And then this waveform is modulated into high frequency and passed to the antenna. At the receiver, we do demodulation. We assuming that modulation and demodulation has been performed perfectly. So therefore, a receiver here, this is our receiver that equals to SMT. If we don't consider noise, that RT equals to SMT. Whatever transmitted here, we receive at the receiver perfectly. There shouldn't be any error. Now we're adding the noise term now. So this is AWGN, the additive wide Gaussian noise term. And this model is called baseband model, because the signal has to bring back to the baseband after the demodulation already. Next, let's discuss the optimal receiver to minimize the probability error. Such receiver is the correlation receiver. We assume that the binary antipodal signal being transmitted. Antipodal, that's the pulse amplitude modulation. Example of this, S1T and S2T. You can see this pulse and this pulse, that's antipodal. Now we use geometric representation of those pulses. Yes, MT, that's the pulses, equals to the coefficient multiplied by the base function psi. S1, the coefficient, S1 is square root EB, and S2, the coefficient, that's minus square root EB. Now we plug in the signal SMT into the receiver signal. So SMT equals to SM psi t plus NT. What's the time t duration? Time t is from 0 to TB. What is a psi? Psi orthogonal base function is rectangular. That's TB duration. The magnitude is square root 1 over TB. So the energy contained in this space is 1. At the receiver, we're going to multiply by this base function first, and then we do integral. And then at TB, I sample the signal. Based on the sample signal, we're going to make a decision Is it 0 is transmitted or 1 is transmitted? I mean digital 0 and digital 1. So this is the structure of the correlator receiver. It's called correlator. Is the correlation receiver. Let's look at the output at this integral here. I call it y of t. Y of t is a time of t, because this is with time going, I do integral. That's equals to r tau multiplied by psi tau. I do not use t here. I do not use t here because there's a t here to avoid confusion. R tau, plug it in, that equals to Sm psi tau. Here t is replaced by tau, and nt becomes n tau, and psi tau is here. Do the multiplication term by term. So therefore, this is Sm psi squared tau, and plus this n tau and psi tau, you do integral. Next, let's look at the value at Tb. This, the output. Next, I do supple. I obtain the value at Tb for y of t. This is a waveform. Eventually, we want to look at the value at Tb, because Tb is a duration of transmit 1 bit. We need to make decision, is this a bit is 0 or 1? We want to look at the value of this output at Tb. We replace all the small t by big Tb here, everything. And if we look at this is a constant because Sm is not function of time, it's a constant. That's the coefficient for geometric representation here. That's S1, this is S2. So we take Sm out. M equals 1 or 2. Now this integral from 0 to Tb psi squared. This is a base function, and this is the energy. We have Sm. That's because of the unit energy content in the base function. So now this is a benefit to represent using the geometric representation with the coefficient and with the base function, because at the receiver we multiply by this base function, and this base function has a unit energy, and then this term n tau multiplied by psi tau, this is a definite integral. It becomes a value. I call it n. So this is a value at Tb at the end of the pulse duration. Next, let's look at this n, the property of n. And this n equals to this integral. And this quantity n is Gaussian because n of t is a Gaussian random process. So therefore, at any time instant, this random process become a Gaussian random variable. Therefore, at time tau, n of tau become a random variable. And this random variable multiplied by another constant, that's psi tau. This is not random. And then we do integral. An integral is eventually a summation. Therefore, this whole term is a linear combination of Gaussian random variable. And linear combination of Gaussian random variables still a Gaussian. Therefore, n is a Gaussian random variable. If it is a Gaussian random variable, we only need to obtain the mean and the variance. The mean of n goes to expectation of this integral from Tb and n of tau and psi of tau, d of tau. N of tau is random. In psi tau, psi everything that is constant. So therefore, this expectation is with respect to n of tau. But n of t is a random process with zero mean. That's the model for our white Gaussian noise. There's zero mean. Then this expectation equals to 0 as well because of the mean of n of tau is equals to 0. Next, let's look at the variance of n that equals to expectation of n squared and minus expectation of n squared. But because of the mean of n is equal to 0, so we only need to evaluate this term. I have a typo here. It should be Gaussian random variable here. Now I want to find the variance of n just equals to expectation of n squared because the mean is 0. So this is n, one integral, this is n. I used another 2 different dummy variables inside the integral to avoid the confusion. I take in this double integral out, expectation take in is psi tau, psi u, n tau, n u. This is double integral here. Again, expectation is respect to this random variables here. So this random expectation are here. Now let's recall the noise is a white process with the power spectral density is n naught divided by 2 everywhere. So this is the power spectral density, this frequency. And the power spectral density is a Fourier transform of the autocorrelation. So this is an autocorrelation. If we take a Fourier transform, this is a constant Fourier transform of constant. The time domain function is a delta function, and the scalar is here. And R tau autocorrelation, the expectation of this random process in at t plus tau multiplied by t, we take expectation. So this tau is the difference of this 2-time instant, t plus tau and t. So the difference is tau. So do not confuse this tau with the integral, dummy integral. We have it here. We have a tau here. This is a dummy variable. You can use any other. We can use v. It doesn't matter. Expectation of n tau multiplied by nu. This is autocorrelation. The time difference is tau minus u. That's the delta function. And scalar is here. That's the power spectral density. The expectation, this term is replaced by this term. So I have it here. So this is a double integral still here. I take n naught divided by 2 out, this constant here. I take this constant here out here. So this is double integral still here and still here. Now we want to recall a property of delta function. So if we want to do integral from minus infinity to infinity, anytime function phi of t multiplied by shifted delta, what do we have? We have the value of phi at t naught here. And this is extracting values at t naught. This is a property of delta function. Now we want to use this property, but we have the integral from not from minus infinity to infinity, but from 0 to tb. However, we know this is psi tau. This is a base function. It has 0 values outside 0 to tb. Now let's look at the integral of tau. This is a double integral. Now I want to integrate tau out. So this is a integrand related with tau, and this is related with tau. Now this integral is related with tau from 0 to tb actually equals to for this integral from minus infinity to infinity, because of psi tau equals 0 outside 0 to tb. Therefore, I can use this property. This integral becomes actually psi u, t naught as a row of u here. And now integral with respect to tau can be integral out equals to psi tau. There is a psi tau here, there's psi tau there. So therefore, from here to here, this integral becomes, so therefore this integral, I wrote it here, using the property of theta function. So the integral becomes 0 to TB psi tau squared. Psi tau is a base function. This is the energy in the base function that equals to 1. So this equals n naught divided by 2. Now let's do a just recap here. The value of the output at TB, the end of the duration, is equals to ESM plus n. And n is Gaussian, which is zero mean with variance sigma n squared. Sigma n squared, we calculate this by taking expectation of n squared because the mean is 0. So this is one term, n, and this is another n. Take expectation n here into the integrand, and this expectation is with respect to the noise n tau multiplied by nu. Using the property of the white process of the noise, this expectation equals to theta function of tau minus u scaled by the power spectral density scalar n naught divided by 2. Now this is expectation become n naught divided by 2 theta function here. Next, we use the property of theta function to integral tau out, to integral this tau, to integral this tau. So we integral one dimension out. This one dimension using the property of theta function that equals psi u. So now plug it in. We have psi u. One of the psi u come from here. That's there. And psi u squared, if we do integral, that's unit energy for the base function. So therefore, the variance of the noise is n naught divided by 2. So after all of this derivation, we conclude that this n, the noise at the receiver at time instant t of b, is Gaussian with zero mean, the variance n naught divided by 2.